First of all, thank you, Nikos, for the introduction. Also, thank you so much, Professor Davroulis, for this amazing overview that we today will build on top of. We will discuss how we utilize efficient post-training methods, specifically fine-tuning with LoRA. And also we will check some important parts that Professor Davroulis mentioned, such as activation checkpointing. And yeah, this should be a nice overview of this method of low rank adaptation usage on a specific model that we will overview today. First of all, what I want you to do is to make sure that your call-up is set up if you choose to follow us during this session. In order to do so, you need to follow the link that was sent by Nikos in the chat, and you need to copy this specific notebook to your drive, right? We save a copy in the drive. When it's saved, it will open in a new tab that you could own, right? It's on your specific account. You could own, edit, run, and do everything that you need. Please, firstly, make sure that you copied the notebook, and then we will set up the hardware connection that will run all of our experiments, trainings, and everything that we will see in a while.
Roman,
Yes,
if you please show us how to copy on our own drive, just the
yes,
menu of
I
the
will show you
file.
one more time. Yes, you open
Okay,
the original link that was sent in chat, then you press File, then you press Save a copy in Drive, and
nice.
what will happen next is that either there will be a tab that will showcase a suggestion to open a copy, right? Or it
Yes.
will automatically move you to a new file that was created. And you could confirm it by reviewing the name of the file. If you have done it correctly, you should see that here is written copy and the name of the file that was initially written. So
Okay.
you may
And
choose,
also,
yeah.
because this affects all the following, the runtime, to make sure they have a GPU runtime.
Yes, of course. First of all, I want to make sure that everybody who decides to follow us uh, copied the notebook. And if you did so, please write in the chat that you was successful in it.
Yes. Okay.
If yes, we will move on to connecting our hardware to the notebook. Okay, great, done. I see first responses. That's amazing. Then we connect our hardware that Google Cloud provides to us. Actually, today notebook will require only the standard subscription, meaning free subscription. It was done intentionally. So first of all, we will check right how to run and fine tune the model under constrained resources, under 16 gigabytes of GPU memory. And also everybody who has an interest in running this training pipeline, they will be able to do so. And in order to connect, we click nearby this button specifically, and we make sure that we run the GPU processor in this notebook. In order to do so, we click change runtime type, and here we should select specifically T4 GPU. Make sure that CPU is not selected because we always train, of course, our models, as you all know, on GPU, but it's easier to miss this setting. So we should make sure that T4 GPU is selected and we click save. So please do so. And after that, we just click connect. In a few moments, our GPU should be connected to our notebook and we will be ready to go. As you could see here, the status of the connection is present, connecting to T4. It may take up to a minute usually. So let's wait and make sure that everybody went through this procedure. While the hardware is loading, let me introduce the uh, overall structure of today's session. Firstly, we will of course, then load our model, which is Mistral 3 billion parameter reasoning model. If you want, you could copy the name from the notebook and open it on a Hugging Face to see more details in a model card. Here, some architecture facts are present about this model, and also importantly, some notes how the developer itself suggests to do the fine-tuning. So today we are following the suggestions by the developer, and on top of that we introduce the LoRA, so everything would be run correctly. All right, as I could see on my own notebook, the GPU was connected. We could verify it by clicking, and we could see system settings such as amount of RAM that is utilized, amount of GPU that is utilized. You could see here that right now it is idle because we didn't move any model or data to our GPU, and the disk that is also running on the background and saving important memory. All right. Please confirm in the chat as well that you have done so and the hardware is connected. Again, yeah, I see the comments that somebody of you already done it. That's great. But again, if you decide to follow, that's amazing. If you just will listen and look at the lecture, not actively running the notebook, it's also okay. What you decide is better for you in the current circumstances that you have. All right. So what we've done, we connected the hardware and we are ready to go. Every time when we start any pipeline, we should make sure that the hardware is connected correctly. In order to do so, what we do is that we utilize the classic torch function that checks that the CUDA is available, and we have it. So let's do so. Quickly check that the GPU is connected to the notebook, not only confirming it visually through the Google UI, but also through the code. And what you have to see is the status that the CUDA is available. If you see that, that's the first step from where you may launch your trainings, post trainings, and everything else at the point when your GPU is connected.
So Roman, yes, exactly. Actually, this is if you see Torch CUDA is available, then more I believe everything of the rest will run smoothly. I see a lot of done in the chat, which is very good. However, I would like also to ask if anyone has an issue, please write us now. That is the beginning of the hands-on to avoid having difficulties later. So if there is an issue, please feel free to write in the chat.
Yes, it is really important. So we may solve it now at the current step and not to come back for that later.
Okay, I see no issue, so
Yeah.
I guess we can proceed, but yes.
Probably, yeah, that means that nobody faced an issue. Can you please
Can
show
you please?
how to get selected GPU runtime? Yes, of course. For that, on the notebook that is not connected yet, I guess, what you should do is that you should press nearby the connect button, a method change runtime type, right? Here is an arrow, you click it, change runtime type. And here, if you're on a free subscription, as my account here right now, you would have three options: CPU, GPU, and a TPU. We should select T4 GPU, click Save, and after that, click Connect. That's it. It will take around, again, 30 to 40 seconds for GPU to be connected. And as it is connected, you will see the green check and the status of your resources. All right. So as we verified that the CUDA is available, what I suggest you to do next is to click Run All. We'll do that in order not to wait for processes such as model download or model training right? While we will be going through the session. They will download and train on the background. And when we will come up to this section, when the model is downloaded, we will already have the results and proceed through the session more smoothly. So please click Run All, and while we will be going through the session, everything would be run on the background. All right. So, of course, after we imported the CUDA, we import other libraries that will be used for today training. Also, most importantly, since we download the model through Hugging Face method, it will require you to grant access to Hugging Face token. However, we are using open model and we don't need any token, so please don't be scared about this notification. Just click grant access and everything will run smoothly on the background. Right. So regarding the libraries that we will use today, we will use, of course, transformers. It is a library from Hugging Face that allows you to efficiently load different LLM models. We will use accelerate to run our training and to specify important parameters. We will use bits and bytes for specification of quantization that also Professor Davroulis mentioned. It is one of the part that will be highly connected to what Professor mentioned in the lecture. We will use PEFT in order to parameters for the LoRA, low ranking adaptation, part that we will train for the model. In order to manage the datasets more easier and smoothly, there is a great library datasets, and also a few other libraries such as Torch extension and the Hugging Face hub in order to check the datasets, to check the statistics of the models, and also to have the necessary namings of the models present in our code book. All right, so we download all of these libraries, we make sure that everything runs smoothly, and we go to actual import of them. Here, everything is present that was downloaded, datasets, random in order to set the seed and set other important parts so our notebook will be reproducible. We also import the pandas for data management, PyTorch, of course, and from transformers, we import three specific sublibraries and methods which are related directly to the model that we will be training today. Okay, and for the LoRA, we again using PEFT. So it is one of the best libraries to work with LoRA because it allows you to merge the trained adapters with the model itself, just with a few methods. And in the background, it is done really well. So there should be no problem of using PEFT for your specific tasks and for specific implementations. All right, and the final library is matplotlib that we will use for some plotting, right? That is necessary in order to check how well our model trains, how it evaluates, and the statistics related to that in order to perceive it visually. All right, so I guess that we are on the same page. If you run all sections of the notebook, everything should be loaded correctly and then loaded as well. Then we move on to the configuration class that will actually define the main parts of our training. It is a really nice, let's say, habit to use an overall config class because every setting that you have related to your training is specified in one section, and you may change it if necessary, really easily. You may find any bugs that are present also clearly. So I recommend to use a class config from where you will import all of your configuration variables into the pipeline. And it also allows for smooth presentation of all of your configurations for other engineers. And let's go for that. So again, we are using the Mistral 3 billion model, which is reasoning enabled. We specify here the training path that will have our data set that we will process and, let's say, filter. You will see that in a bit. We also specify the validation dataset path, the maximum length of the model. We specify the batch size. We are using, I need to say that there are more parameters that could reach you high accuracy in this training. But in order to be under the cap of 16 gigabytes of memory, we are using these specific parameters that were tested and showcased better performance after the fine-tuning and fitted under the 16 gigabytes cap. But of course, you may increase if you will download this notebook to your own hardware. You may increase such parameters as max length, the batch size, number of steps in order to receive even better results. All right. So the batch size is 4. We will train our model with 30 steps. We will evaluate it 6 times every 5 step. We will do logging as well, also every 5 step. The learning rate, which is related to the LoRA, we specify also right here. The weight decay. I'm sure most of you know what is a weight decay here, but it is a parameter that basically penalizes the weights that are out of normal statistical distribution, which allows for better training. We also do a warm-up ratio for our hardware to be prepared for the training. And then we move on to specific parameters which are related to LoRa, right? I see a message in the chat. Yeah, of course, I could zoom out if you wanted so. Please mention, is it better now? Or maybe somebody can't see the chat, can see the code, and it will be better to keep the previous size. So what do you think? Now? Is it better now, or it was previously better? Okay, many thanks. Good for me. Okay, great. So we will keep the size like that. All right. Yeah, the comments are comprehensive here for you to be able to download again this notebook and run it at your own time and basically dive into details at whatever part you want. So the comments are important and there are a lot of them here. All right. And yeah, we specify specific variables for our LoRa, basically the weights that will be merged with our foundational models, for foundation model of the Mistral, and we will train only that weights. And we specify the parameters that will define the amount of weights and the amount of basically layers that are present in the LoRa with these 3 parameters: LoRa rank, LoRa alpha. LoRa rank specifies basically the size of a matrix related to the LoRa, and LoRa alpha specifies how deep these parameters are merged with the foundational model that we use here. Because the size of a matrix could be the same, but to the extent how these new layers and new weights affect the initial model, it could be different, and it is specified with LoRa alpha. Then we also mentioned the dropout. I'm sure many of you know what is a dropout, but I need to repeat just in case. The dropout for specific learning steps turns off parts of the neurons, so the gradients or basically the training, would be spread more equally among all of the weights, and there will be no part of the model that uh, would be more, let's say, important and would have bigger effect than any other. So the dropout allows us to spread the knowledge in the model more equally. Okay. After that, yeah, we specify the subsets of our data set. Again, it is done here in order for us to be under 1 hour, under 1 hour time for this session. But as you will get familiar with this notebook and you will be able to run it with your own hardware, of course, it would be much better to run on the whole data set when you will be not limited by time. And then we specify the seed again in order to make sure that everything is reproducible. It is really important because when you do the experiments, you may reach a result that is actually not statistically significant and not reproducible. So seed will allow you to share your results among other researchers and among other developers in order to be on the same page, on the same track, and have same capability to adjust the training in a way that it should be. All right, so we specify that class and then we refer to it when we will be defining our trainer and other parts of the training that will require some variables from that class. Okay. Yeah, then we set the seed. We specify the seed for multiple parts of this notebook. We specify that, of course, for the random library, for the torch library, because, of course, for example, when you initialize new matrices, in most of the cases, they're initialized randomly. So you need to specify the seed. Initialization would happen every time, the same for, again, all of the runs of this notebook. Okay. And from that, we could move on to downloading our first data set that we will be using. This data set supports reasoning. It was a critical point of choosing a data set because when you fine-tune a model that supports reasoning, such as in this case, and you fine-tune it on a data set that doesn't have reasoning, you basically decrease capability of the model. And you should take care of it really well because it's a sensible part that will affect your performance a lot. So if you're using reasoning models, make sure that you fine-tune it with a reasoning. If you're using classical models, better to use data sets that do not contain reasoning. So let's open the card of the data set that we are using here. You may do the same. Just copy the link and open it on a Hugging Face. These data sets, both that we are using, present us three important parts that we will use for the training. They present us with a question regarding some medical assessment or medical problem answer that the model should give us, and reasoning steps that the model performed in order to answer that. These data sets, as I know, they contain also synthetic data and real data that was labeled by humans. So reasoning here is really valuable, and it, as we now allow model, not only one, but different models, of course, to get into important parts of a specific domain knowledge, extract this information, and to elaborate on it much better for medical applications. It is really important because reasoning again proved less hallucinations and better ability to answer hard questions. All right. So we load the data set. We load it with the method of Hugging Face. We just basically define the name of the model, and it automatically downloads it from the Hugging Face platform, right? You may see here where we are. Okay, it downloaded well for me. I hope for you as well. And also we specify a split here. We could specify train, we could specify validation dataset if it's present, in order for you to choose any split you want. Really handy approach for the Hugging Face. And then some pre-processing.
Roman, this is
Yes.
loaded now on the fly, right? It is not saved on Colab locally yet.
Yes, the dataset was loaded on the fly, exactly. And for all of our participants, it was done, I hope as well, who ran all of the cells.
Mm.
Yeah.
Yes.
So yeah.
Medical one. Yes, exactly. Is this a question or?
Because no. We have two data sets actually. I think you scroll a bit lower because here we define the second data set, medical O1 row. There was I mentioned that somebody opened uh, a later part of the notebook where we load the second data set. Definitely, you a bit went ahead, but it's true that we will use two data sets because we will merge them and have a much larger data set, which is great because as Professor Davroulis mentioned to us, scaling laws that also contain the amount of data and its quality. And the amount of data and the quality affects the model performance as well. And we want to utilize the scaling laws as best as we can. So more data, and if it's processed well, of course, better performance you have. All right. And how do we process the data in our case? Firstly, of course, we load the data to the pandas in order to be able to do all the necessary steps. Necessary steps that we do with the first data set, right, the MedReason. We extract the necessary information that we need and drop everything else. We save questions, options, chain of thought, and answer to our data frame methods. And most importantly, we drop any rows with missing values, because again, errors affect your training performance really, really deep. And if an error is introduced in the data, you may think that, all right, maybe architecture is not right. Maybe I need to optimize the training, but no. It is really common that the problem of performance is defined by the data quality. So we need sure that any missing values are filtered, that of course any extra spaces are stripped. And in order to do the training, of course, everything should be saved as strings. So nothing special here, but we just pre-process basic possible mistakes, and we save clear data frames of the values that are present right here.
Perhaps we can preview a couple of rows of the DFMed of the data
Yes,
trace.
of course, we will review. They will be present in a bit
We have it
in
later.
higher
Okay.
detail. Yes. Then we also check how many rows was dropped, because we, of course, need to understand the quality of the data. Here we made sure that we selected the right data set and no columns and no rows was dropped, which is important because you should, even if you select the great source as we did now, this data set is academically established, there still could be some problems introduced, so better to double check everything. But when you see that nothing was dropped, it is amazing to understand that the work that was done by others could be used um, freely.
We have one question.
Yes, can you please show how we connect again to the web data? how we connect to the web data. I'm not sure what you mean by that. How we connect to the web
guess
data.
the Hugging Face data set. Actually, this is in the previous cells. There, yes, because we use LoRA data set from Hugging Face Hub. It is downloaded automatically, right?
Yes, it's downloaded automatically, and we even do not connect to it directly. We just use the method load dataset. And if you imported the Hugging Face, I guess you did it, right? If you run all of the cells sequentially, then what you do is that you just run this method with specification of your dataset, and everything is saved and downloaded. That's what should be present. All right, we just confirmed that no errors was present in the data, which is amazing. Again, thank you so much for amazing work of MedReason team. And then what we do is that we move on to the second dataset, which is also reasoning dataset. Let's open up it here. It has an easier structure where we have the direct division to three parts that we will need, to a question, to a chain of thought, and the response. Again, as I know, this data is partially constructed from synthetic data and from data collected directly from professionals. So again, really well-defined data set, has a lot of followers and downloads. So every time when you select your data sets on what your model will be dependent, make sure that they are coming from verified sources. Side note, there could be present, if you download not from verified sources, even parts of the dataset that could spoil your model, basically introduce some security dangers into how well your model performs and how well it answers some specific questions. So if you want to make sure that no risk exists, please always verify the sources from where you select datasets for the training. Yes, thank you, Nikos, for sharing it in
I'm
the
also
chat.
sharing the links. Yes.
Okay, so we select in the same way with the load dataset. We specify the name of the second dataset. We train it, we then load it. Because it contains actually parts of the dataset with different language, you also may specify the part that you need. Here we specify that we need English part. And yeah, we download the model, we download the dataset, and if you see this green statuses, that means that the download was correct and everything is ready for us to actually set the stage for the training. But before, we have to, of course, pre-process the dataset in the same manner as we did with the previous one. We define the columns, the column names that we will rename, because in comparison to previous dataset, right? Here, the names was already present in a way that we will need. There was question specified, options, and the answer. So in a manner that we need. Here we will need to rename it because, as you could see here, they're starting from the capitalized letters and also have some additional symbols. So we need to make sure that everything's named correctly. We rename the columns. Again, we drop null values, make sure that any extra spaces are stripped, and we save everything as a string. So it will be parsable by our model. And here you could see also that no rows was dropped. But again, even if you download the model from verified source, please verify everything yourself, as we do here now, right? So where we are, we have two datasets that was pre-processed, and each of them contains three parts: question, chain of thought, and the answer. Exactly the parts that we will need for the training. After that, we merge the datasets. And we do that basically just with concatenation. And we ensure that any duplicates are dropped, because they could happen that if the datasets are large and were released in the same time, there could be some duplicates, right? And we don't need them. So we make sure that no duplicates are present. And also we convert back after everything that we've done to our Hugging Face dataset. We do that with the extension from pandas of the method dataset, and we save it in a unified dataset, again, that is of a type Hugging Face. And let's see what we have got in the end, right? How our dataset is structured in low precision. We have a question, right? Such as, does preoperative measurement of heart rate variability predict hypertension during general anesthesia? And the question contains two possible answers, yes or no. That's the first part of our dataset. Then we have chain of thought that goes up to here. Basically, it goes step by step how such questions should be answered, what are important knowledge that should be taken into consideration for this answer, for answer production, and the final answer that the model outputs to a user, right? The final decision is yes. Spectral analysis of HRV is a sensitive method for detecting individuals who may be at risk, and so on and on, right? That's how our dataset is structured in its detail, right? We have again question, chain of thought, and the answer. However, we will need to do one more thing. We will transform our dataset to a JSON format. We do that with train. First of all, we define our dataset that we saved right here, right? And we use the method toJSON and specify the path where this JSON file would be saved. A practice to save the dataset in JSON format, again, is really well established, because you could basically skip all of the data processing steps next time and load the whole dataset more easily to a new model, or to send this dataset to your developer team. And what this team would need to do is just to load the dataset. Nothing else should be present, and the JSON format is really easy parsable. So even no such libraries as pandas should be introduced after the steps are done. All right.
Roman, sorry for interrupting again. Let's make a pause here. So now we can view our dataset in our local folder, local directory on Colab, right?
Yes,
Uh,
exactly. Exactly. It should be right here.
in
Data.
data, yes. Or if you are running on your own compute, you can view it there in the relative path. And I would like once again to ask for a confirmation from the audience that you have the data set, you understand what is happening. We have three parts: question, chain of thought, and answer. So please give us a like or a question. If you, yes, that's
Yes, let's see. And it will be a really
nice.
nice step if you have any problem to fix it right here, because after that we have training, right? And if there is any problem with the data set, it should definitely be fixed before our training procedure. Okay, I see in the chat nobody mentioned any problem. I hope because everything ran correctly.
Yes, only likes and hearts, Roman. So I guess
Okay,
everything is fine. Yes,
okay, nice, great.
thank you.
Yeah, so, and as we saved our datasets with the JSON format and they're present in your directory, what we do next is we define our data files object that contains basically two datasets, one for training and one for validation. It is a necessary structure in order for the Hugging Face method load dataset to work, because what you do is that you use load dataset, you specify the format that is required, and you specify this variable that contains training and validation dataset, and you save it in one Hugging Face format from the load dataset method. And exactly this would be used for our training, exactly this variable, raw datasets. Then again, as we mentioned when we were observing the config part, for training purposes, we restrict our dataset to a subsize, to a subset. But when you will be running, if you will have a chance to run this notebook with a larger amount of computation and larger amount of time that you possess, you may train on a whole data set. We checked it previously on a larger, again, computational resources that the performance scales and yeah, with larger parts of this merged data set, you get better performance. Okay. After that, we go to most important parts of this training. We download the tokenizer. As again, you heard from the previous lecture of Professor Davroulis, what we do is after our dataset is ready, firstly, we transform it to the tokens. Tokens are actually the only information that is understandable by large language models, right? If you pass the text directly, nothing happens, but if you transform it to tokens, that's where magic starts. Yeah, we download the auto tokenizer. We specify what kind of tokenizer do we specifically need, because for different models, there are different tokenizers. And we do that by specifying the name of the model. It's saved, the model saved in our config file. And also Mistral models known for having some specific tokenization settings that should be addressed. And for that, we specify parameters such as this in order to not have any errors during the training, because still you could train the model without that parameter, but some inconsistencies could be inserted if you do not use the fixed Mistral regex. Make sure that every time you use Mistral models, you specify that. All right. And we may see also some specific tokens that we will use that will be used during the trainings, such as end of sequence token, right? Padding token. These tokens are inserted into the data in order for the large language model to signal where a training sequence or sequence that should be generated ends. And also padding token, because if your sequence of tokens that you train on or generate is less than the maximum amount of tokens that you specified as max length variable, here I reminded you we specified 256. So for example, if your sequence is 200 tokens, 56 remaining tokens would be filled with padding, and padding token, and it is necessary in order to keep the correct size of each sequence and also allow for some parallelism computation that is present on an architectural level of LLMs. After that, we load the model. Actually, we then load it from the Hugging Face in the same way as we did with the datasets, but here we use specific method to do so. We specify the method that Mistral developer team created, which is related directly to their models. If you're using other models, there will be different methods. And you specify the name of the model that we'll use. You specify that we will use the pre-trained model, exact name that is same in the config, and the quantization parameter. Why it is important? Because quantization, some developers release the models of different precision, right? Of different precision levels. And if you specify this, unspecify this part, you may thought that, all right, I downloaded the BF16, I will be able to do some parallelization or training, but it happened, for example, that you download the model in a precision of 4 or 8. And in this case, most likely your pipeline that you created for the training will not work. So make sure that you download not only the correct model, but you also download the correct precision of this model, right? So here we download floating point 16. That's the model we will use. It takes 7.7 gigabytes on your hard drive. Again, it's just 3 billion model, great for small tasks and edge devices. For example, it is highly likely that if you have a smartphone of one of the last generations, that this model could be run on your smartphone locally, which is great. And there are more and more such use cases in the industry that are developed. All right, so we loaded the model. We downloaded the model. We will load it a bit later. And now we specify the LoRa configuration file, right? LoRa, it presents itself as additional matrices, additional weights that you merge with your foundational model that you decided to use. What does it mean directly? It means that you never touch the original weights of the model that you downloaded. You do not change them, you do not train them. What you do is that you just train the adapter, right? Low ranking adapter, LoRa, and add them to the original model, to original weights. This method allows you to do many interesting things with your correct task, exact task at hand. For example, you may have one base model, but different trained adapters, right? And in this case, what you will do is that, for example, you have adapter for medical purposes, adapter for psychological purposes, right? And you have one model. And in this case, maybe you have a chatbot that serves people with questions related to psychology and questions related to more medical questions. And in this case, you just have one original model. And when your chatbot recognizes that the question related to some specific part, psychology or medicine, you choose the adapter that you will use for this specific chat. And it saves a lot of memory, not only during the training, but also during the inference. Yeah, and you could set up such things really easily. And it is amazing that such uh, such configuration and adapters were developed. All right. And in a configuration of our LoRa, we specify the rank of the LoRa that we defined in a config file. we specify the scaling factor, meaning how deep the adapter parameters will be inserted in our model, the dropout, the bias. It affects the training performance, basically the bias term, right, of training and the weights. But here, to save our memory, we keep the bias not trainable, which also showcases the training performance that is sufficient for today's session. We specify the task type because LoRA, of course, could be applied not only to large language models, but also for diffusion models, for models related to multi-model capabilities. But here we define that we just need the casual LM, which mentions that this LoRA would be applied to language model. And below, we mention the exact modules, the exact layers where our adapters would be introduced. We introduce the adapters here to two parts. We introduce them to attention heads and to multi-layer perceptron part of our layer of our network, which basically in this implementation puts the LoRa adapters on most of the layers present in the network. There are also cases when LoRa is applied only to attention mechanism of a model. It is a way to reduce the computation that is required for the training and keep sufficient performance, basically the trade-off, right, between the amount of memory that you use and the performance that you get. But if you have the constrained resources, better to just apply LoRa to attention part of your large language model. Okay. After that, as we specified the LoRa configuration, what we do is with the PEFT library, we specify how our model is merged together between the LoRa and the model itself. So with the method getPEFT model, we mentioned the original model that we defined previously and loaded, the Mistral, and our LoRa config. And from this point, our model variable would refer to a merged model, to a model that is united together. In order to allow, right, our frozen layers of the original model to still pass the gradients that are required for the training, we enable the gradient flow with the method enable input require grads, because if you will not do so, the frozen layers of your model will not propagate to the LoRa adapters, and yeah, nothing would be trainable in this case. And another method for efficient fine-tuning is that we allow for gradient checkpointing. If you remember from the lecture of Professor Davroulis, there are two possibilities, right? If you save your checkpoints, your gradients during the forward pass of the model and reuse them during the backward pass of the model, or what you do is you basically drop them as the forward pass happened and recompute them actively during the back propagation step, which requires basically, right, more computation in this case, but saves a lot of memory. I saw a question in the chat: how similar or different this fine-tuning pipeline collab be for other modalities, image or audio? Nice question. The LoRa configuration file and the PEFT libraries, they are universal, and that's great. In this way, you will just change the layers to what you will apply your adapters, and also you will change the task type in the LoRa configuration file. Right? That would be the main changes of the LoRa config. However, all of the pre-processing parts, right, that we've done on our language dataset would be completely different for a task. Also, what model, of course, that you download would be completely different. So I would say that from this notebook, you might take the core parts which are related to the LoRa, to configuration part of the notebook, and also to the way how the training happens that we will see in a few cells below. But all of the pre-processing, all of the data download, all of the model specification should be different. So you will definitely have valuable insights from here, but a lot of parts will need to be changed. All right.
Um,
We,
I don't
yes,
know if you mentioned it, Roman. I think the main change is the tokenizer, where you need an image at least for images, instead of the
yes,
tokenizer. Yes.
you're completely right, Nikos. Yeah, we will need different tokenizer because images are tokenized in a different way. We take pixels as ground information and transform them to tokens. You're completely right. I forgot to mention that. Yeah, make sure that the tokenizer uh, is set up correctly in this way. Okay, so we may see here that trainable parameters that are related to the LoRa, right there, 33 million, closer to 34. And the original model parameters plus the LoRa are 3.8 billion. So we actually train a bit less than 1%, but still, as you will see later, we'll have improvement on our data set and on our specific domain, which is great, right? We save a lot of resources. We just train 1% of the parameters, around 1%, but we gain in performance and in a domain knowledge that is necessary for our case. Okay, then we move our model. Again, that I reminding you, our model right now consists of the LoRa and the original weights. We move our LoRa model to GPU and basically check how many parameters are present one more time. So 3.8 billion parameters. Then we see how much memory was allocated and is allocated still when we train the model, when we load the model. We do that by accessing our CUDA layer through the PyTorch library, and we use the method memory allocated. If you will go to your resources, you may see here as well that, just a second, that the GPU RAM is around 7.7 gigabytes out of 15. And it's not the full 15 gigabytes as it were during the training because the training already happened. And what we still have on our GPU is just the model itself that sits there after the training cells were run that we'll see in a bit. But when the model was loaded, again, it took 7.8 gigabytes of our GPU RAM. And as you could see here, it is much better to utilize such low-level methods than just rely on the overall statistics that could be present by Google Colab or any other UI interface, because it gives you much higher precision of your utilization of where in terms of memory your GPU stand. Okay, so yes, let me come back here. Yeah, we made sure how much memory we allocated, and we go for formatting our dataset and its tokenization in order to feed it in our model. For that, we define specific function that will take all of our dataset and will restructure it into the tokens format that we will pass in our model. We do that by iterating through our text, through our dataset, and we save again the question, chain of thought, and the answer. We unpack them from our dataset that we saved before, and we pass them in a format that is related to our model, specific model that we have chosen. And we unite them in a one continuous text, right? We have question, then we insert the exact question from the data set, then we insert the chain of thought, and pay attention here because we insert it in the thinking brackets. That's how the Mistral specifies their thinking tokens should be inserted for the training, right? We specify start of the thinking sequence, end of the sequence of the thinking sequence, and between that we insert our chain of thought, and then we present the answer. Right, and in the end of our text, importantly, we add the end of sequence token, right? So our model will know that here the answer should end, and basically it should stop produce next tokens. After we produce this function, it's not finished yet, because in this function, what we do is that we also tokenize, of course, the inputs after the text were appended and structured in the correct way. We do the tokenization. We specify all of our sequences. We do the truncation. Basically, if any sequence is higher than our max length, it will delete the extra tokens in order not to break our training, right? Here we specify also the maximum length and additional parameter that we don't return the tensors because we will need only input IDs and attention mask that is present right here. In the inputs IDs, after encoding happened, we have actual tokens that are present right here. We'll go into detail how they're structured in a bit, right? So after our encoding happened, we get the variable of input IDs, tokens, were transformed from our word sequences, and we get the attention mask. Basically, attention masks consists only either of 1 or 0. 1 stands for real token and 0 for the padding. Basically, if we have here in the end, right, 0 stands for the padding. If we have here additional end of padding tokens, in attention mask, we should mention that they are not real tokens that our model should not pay attention to. And they should not affect anyhow the next generated tokens. And specifically for Mistral model type, we also need to add for end of sequence tokens value of -100, right? Because in this way, internal method of cross entropy will not pay attention to not needed tokens, right, to padded tokens, and again the computation would not be affected to the tokens which were inserted above our length of the word that were mentioned in a prompt or in a dataset. Okay, and after that we return the encoded variable that consists of input IDs, the attention mask, and the labels. And we return these three parts. As we defined this method, we tokenize our validation and training datasets. And now we even drop the columns, right? No text exists anymore in our dataset. What we have is only the tokens and the attention mask. So here we have an example of our dataset. There are 5 tokens present from a sequence of previously what was words, right? Now they're just tokens. And also attention mask, as you see, these all are real tokens, and in attention mask they're specified as one, meaning that the model should pay attention to them, right? And also labels, which are same as IDs, basically the tokens, because there was no padding token and no -100 value was introduced. And yeah, basically here we see only the actual tokens, not the extra tokens that was added. And in order for our dataset to be parsable, we transform it to the PyTorch format, and we are ready to feed our dataset to our model, right? The dataset contains inputs IDs, attention mask, and the labels. That's what we have after all of the work that we have done. Okay, because of the time, the runtime was disconnected, but it's okay because we already ran everything that we needed. I hope you as well, and if same issue appeared on your device, nothing was affected. Okay, also we specify where our model would be saved, the checkpoints, so we will may access it later. All right, and the most important part is the actual trainer, right? We specified before the LoRA configuration, and now we specify how the LoRA configuration would be trained. Here we mention the batch size, mention the per device batch size. This is kept intentional here because if you will decide to run this notebook on a few GPUs, you may decide to do parallelization, and so to have larger batches on your different GPUs. Then we specify maximum amount of steps for the training, the learning rate, the weights decay, warm-up ratio, everything that we observed in a configuration file in the very beginning. Again, we turn on the gradient checkpointing, as we mentioned, as another efficient way to do the fine-tuning. During the backward pass, the checkpointing would be calculated on the go. We specify what kind of precision we will use, PF16, same as our model, and the logging strategy, right? How often we will showcase the training statistics during our training method, and evaluation parts as well. After you run the cell, your settings are repeated in a command line, which is great and handy. And we specify the final thing that is important, right? The final step before the training is in our trainer goes the model, the arguments for the training that we define above, the dataset, the tokenized one, and the evaluation dataset that we tokenized as well. Before our training, we do the evaluation to understand what kind of flaws do we have on our evaluation dataset before running the training procedure. As you could see here, before fine-tuning, we have 2.01 evaluation loss. But during the training itself, on our 30 steps, you may see that just, I'm reminding you, we trained less than 1% of the model parameters, right? And we were able to reduce the validation loss from 2.01 to 1.38 because the actual training here happened, right? We trained our model, evaluated every 5 steps. There were 30 steps in total. And with that small training, because again, we were under 16 gigabytes of the GPU, we trained only 1%, less than 1% of the total model weights. And we were able, for our specific domain knowledge, to decrease the validation loss significantly from 2.0 to 1.38. And again, we were constrained here by our session time. If you would decide to train it longer, you may reach higher results, but be careful also of possibility of right basically feeding your model too much and in the end having some increase in the validation loss if your model would basically remember all of your data. So you should find the middle golden ratio between small number of steps for the training and the large amount in order not to overfit the model, how we say that. Okay. After that, we plot our train and validation loss. I see some questions. In your experience, how important is the choice of optimizer for fine-tuning tasks like this? The optimizer, I think, is definitely important, but most important is the way, because everybody right now kind of agreed that Adam optimizer is the state of the art, right? And less experiments are done with what kind of optimizer do we choose, because there was an agreement, let's say, within our uh, training community, training developer teams, and etc. But what is more important is the architectural decisions, in this case of your adapters. If you will decide to, for example, how we discussed before, to apply your adapters only to attention layers or to layers of the whole network, that's where most of the change in the performance will occur. So, and that's exactly what you're responsible for while applying the LoRA model that we observe here. I would pay more attention to that. And of course, I guess if we will have a new widely adopted optimizer, everybody would get notified immediately, because yeah, current standard of Adam optimizer is present, but something could change and we definitely have to pay attention to that, because nothing moves that fast as AI sphere, definitely. Okay, so I hope I answered your question. And here we see the training and evaluation loss. The evaluation exactly followed, not exactly, but the uh, high structure of the training loss was the same as evaluation loss. And as we see, the model did not overfit, which is great. And we decreased our evaluation loss to around 1.38 right, loss, which is great for less than 1% of training parameters. Then we save our model, and we save here only the optimizer, no, not the optimizer, sorry. We save here only the adapter, the LoRa adapters, and we don't save the original model because we didn't touch it. I'm reminding you, as it was when we downloaded, it is in the same condition right now. What we have done is that we only trained the LoRa layers, and right now we have the ability to merge them during the inference or to keep them apart and to inference, for example, only classical model, which is also provides you a lot of flexibility for your actual tasks in your exact domain that you may have. Okay, so after we have done with the training, we empty any cache that may have still left in your hardware, a good practice. And after that, what we do is we will actually do some inference, right, with our model. In this way, we switch to the part of actually doing the inference with the model that you trained with LoRa. How you do that? You firstly load your foundation model in the same way as it was before, right? Again, it's Mistral 3 billion. And after that, with the PEFT method, we merge our LoRA adapters and the foundational model for the inference right now, and we move it to our device. And that's exactly showcase what you will be doing as an inference engineer, basically after the training was done. Here you could imagine that you could have a few different LoRa adapters, and based on your task, you merge different LoRa adapters that you may be required to use. Again, for such tasks as medicine or for such tasks as psychology, for example. Then we specify the prompt, right? We ask the question, we showcase that we would like to receive thinking steps, right? And the response would be generated. I think most of you know how we do the inference. I will not go into much detail because we are limited already by time. So we just specify basically the temperature, the P parameter that defines how repeatable basically our inference tokens that are generated are. We specify the padding token and the repetition penalty. So our model would not repeat itself and there would be no inference loops basically when it may decide to output the same token a few times. Right. We set up this inference settings. And again, after the inference, as you remember, what we get always is only the tokens, and we need to also decode them. So with the tokenizer that we use, we decode our tokens in the same method that is responsible for response generation. That's basically always how you define your inference and how you output the model. The model answers is based on your specific application. Here, most likely you will change it in order to adhere to your own application, but on a high level, we just divide the answer on a question, on a reasoning tokens and on answers, so it will be clearly seen in our output. And let's see what we have here. You have a question, the answer choices, the ground truth that was present in a data set. And after that, we may see the reasoning that's happened in a model, right? The model decided that it should need to understand in detail some specific medical related knowledge and should kind of comprehend it before answering the question. It reached the conclusion after that with a final answer B. And it is exactly our trained model. That's how our trained model behaves right now. It goes deeply into medical knowledge. It goes deeply into reasoning steps, which can prove to decrease hallucinations. But if we will compare to our base model, what we could see is that it doesn't have this exact structure that we may need for purposes of explainability, transparency. Maybe our patients would need to dive into details of the reasoning, right? Which is highly common in critical use cases. With the fine-tune model, it is possible to do because our fine-tune model learned all of the specific reasoning parts, right? How it should output itself and how it should think. But our base model, 3 billion model of Mistral, outputs our answer without any, let's say, clear differences between the reasoning and also without clear details of how it should comprehend and unite medical knowledge. However, it still reaches the answer that is required the answer B. But again, for explainability purposes and for purposes of transparency of the model, we definitely may see that our fine-tuned version is much better. All right, so this part of the notebook is for any for your error debugging. If you will run this model step by step and something not run, you just uncomment this section, run it one more time, you clear all of your resources, and you're good to go from the beginning of this notebook by yourself without any problems. So yeah, I hope it was really clear. I hope you find a lot of insights for that. I see
Yes.
that there are some
Thank you, Roman. Let
questions.
me make a wrap up because
Yes.
we are really running out of time. Uh, First of all, I would like to highlight two things. The first is that for this small model, this small compute power, we can see that the evaluation loss is decreasing. Okay, so this is like very difficult to attain. The second thing is that the fine-tuned model indeed performs reasoning and medical reasoning. Okay, of course, we need to highlight that this is not a production model ready for production. This is just for experimentation and for understanding the method that we use. However, we will do more trainings on September, most probably after holidays, on FSDP for a bigger Mistral model and much bigger compute power. Roman will briefly present you now experiments from Luxina with 12 GPUs in parallel, and we will have a dedicated training after holidays. Having said that, I have shared in the chat the subscribe form for our training events for PHAROS newsletter. So you may put your email there and get notifications. And also a link for the evaluations. This is very important for us to evaluate the course and in order to receive feedback and also for our resources, sorry, reporting. Now, regarding the question, my model answered A, yes, like I said, this is not, you can never be sure 100% that the model will behave correctly. That's why we have evals. We did a course on evals in the 11th, in the 10th course with RAG, but we will try to do more on that as well.
Yes, and here where clear reasoning exactly shines, because if your model outputted the incorrect answer, what you may see is exactly the steps how this answer was retrieved and why the model decided exactly on that. So here explainability and transparency that we reached with fine-tuning exactly on reasoning datasets in a medical domain is really important.
Yes. One more question. Is there the possibility regarding the fine-tuned or base? I think it's the fine-tuned. Yes, again, despite Roman set the seed parameter 42 in order to have reproducible results, we don't have always reproducible results with LLMs because they have other sources of randomness. So this is one of the problems. How we treat this with evaluations and with human in the loop. It is not only the model. You cannot take serious medical decisions only with models. We will have more trainings on these matters, so please stay tuned. Okay, thank you, Christos. Is there the possibility of a more unsupervised fine-tuning? More unsupervised fine-tuning, like a model is fed with additional data and adapts on its own based. Yes, of course, we can do that. 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 We can do that And that's been shown
Yes, it is absolutely possible. It requires reinforcement learning part on verifiable tasks. For example, that's what was introduced by DeepSeek, if I'm not wrong, when they used and trained the model that was really well performing on math tasks. And what they have done is that because the math is verifiable part, right? And you may reach the exact answer and check that it is correct. What they were doing, they were optimizing their reasoning, and it was done, how you mentioned, in an unsupervised way, until the point when the fine tuning of its reasoning, of the model reasoning, was performing much better on these verifiable tasks. So without any human input, right, the model were adjusting its way of thinking by itself. So yeah, that's the way how it is done. And for its time, it was groundbreaking. Now, a lot of labs, not, let's say, uh, AI developers which are related to some specific companies, because if you want to get your fine-tuned agent, I don't know, for traveling agency, right? There are so less verifiable tasks that you may use this reinforcement learning pipeline on. So it is mostly used when we do the post-training of models before the final release. That's when it is done.